Shall we wait for the boss? The boss is not here. The boss is not here. Okay, I think we should start. So, good morning. Before we start the second part of the course, I want to recap what I told you last week. And so at some point you may have to listen very carefully because there is not much chalk anymore, so maybe I will stop writing and just talk to you, and we'll see what happens. So recall, we did two things. In the first 4 lectures, there was 2 lectures. No, there is enough chalk for everyone. It will fit, I think. Maybe the second course will be problematic, but the first one will work. Maybe it will end up in yellow. So there was a deterministic part, which was Löwner's equation. And I did it in 2 cases. The caudal case, and I just want to rewrite the equation. So this was the conformal map GT, mapping the complement of a curve up to time t back to the upper half plane, mapping gamma t to beta t, which was the image of gamma t. And then we had normalized the map to have gt of z equal to z plus 2t of z plus other terms at infinity. And then there was the Löwner's equation, which was the time derivative of gt of z equal to 2 over gt of z minus beta t. So this was the first half of the deterministic part. The second half was about the radial case. So in the radial case, there was a curve going into the disk from 1, like this. Again, gt mapping this back to the disk. And then the normalization was given by saying that gt of 0 is equal to 0 and gt prime of 0 positive. And then the Löwner equation was very similar, but the vector field was a bit different because of the topology, which was dt gt of z was equal to e to the I beta t plus gt of z divided by e to the I beta t minus gt of z times gt of z. So that was the deterministic part, and it took the last 2 lectures. And then there was the probabilistic part that was a way to justify that in a scaling limit we would expect the family of maps GT to satisfy 2 additional properties. So from probability, we were expecting the domain Markov property, which was saying that if a condition by the beginning of an exploration path, what you see in the future is exactly the exploration path in the domain that was determined by the first part of the path. So that was essentially the same as the Gibbs property for spin measure, for instance. And something which was essential was conformal invariance. And this I told you more or less how to derive it in the case of percolation. And I argued, and I'm not sure I was convincing, for the case of the loop Hera's random walk, that it was reasonable to hope that there would be conformal invariance in the scaling limit. And then, once you have the formalism of Löwner's equations and these 2 properties for the expected scaling limit of a discrete model, then it's natural to look at SLE kappa, which is obtained by solving Löwner's equation with beta t equal to square root of kappa times bt. So the statement was, if there is a scaling limit and this scaling limit is conformally invariant, then it is given by Löwner's equation and beta t has to be Brennan motion up to a linear time change. So that was more or less the contents of the first week, and now we are going to do 2 things. So we have 2 goals in what remains. So first is study SLE kappa itself. So now we have a natural definition. We have a natural one-parameter family of processes, and we can look at them as processes and see what we can tell about them. And the second part, which is maybe more interesting but much more difficult, is to start from SLE and go back to discrete models and derive information about discrete models. So back to discrete models. So before I start the real contents of the course today, I updated the lecture notes a little bit, so they are on my web page. If you look at the first page of what you got on the first day, there is an address, and you can download the new version as I go. So it's growing very slowly, but there is something new about what I will say today. Okay, so I don't know if probably chapter something, n+1. So remember, the point was that we started with a curve, and we obtained Loeffner's equation. But now we want to go backwards, so we want to start with beta, which is square root of kappa times Brownian motion. And let's say I will look at what happens in the upper half plane. We want to solve Loeffner's equation. And I argued that you can always solve. So you take beta t equals to square root of kappa times bt. And you can solve the equation over there. This you can always do, and you get a family gt for positive t, which is the flow of this ordinary differential equation. The flow of y prime equal to 2 over y minus beta. And so these give you conformal maps from some domain ht contained in the upper half plane back to ht, back to h. And I explained to you why this was onto, because you can always reverse the flow and start from any point in h and move the flow backwards and find the starting point from which you arrive wherever you want. So this is actually a bijection. It's conformal because the vector field is a conformal function of g here. And so what you can say is that ht is the same as h minus some compact set kt. So this defines for you a growing family of compact sets. So kt is growing because kt is the set of these such that you cannot solve the solution up to time t. So this is something I already said on Friday. That's why I'm going a little bit fast here. So formally, it's not exactly clear what SLE means. If it means the set of GT, if it means the set of KT, or if it means the curve, but essentially it's the same information. And the whole story here was saying that it is the same information. You don't gain anything or you don't lose anything by going from GT to gamma t. So the first proposition, well, maybe it's a theorem, says that, so if you remember what I told you on Friday, if you look at a Loeffner chain like this, there are three possible regimes. It can be either a curve or generated by a curve by filling the loops, or it can be pathological in the sense that there is no curve and you add stuff which is not localized at some times. And the theorem is that SLE is almost surely generated by a curve. So there is gamma t maybe not inside the upper half plane, but maybe on the boundary, which generates the compact set kt by filling the loops, if there are loops. And this is called typically the trace of SLE kappa. So it's a continuous curve, and the proof of this theorem is very technical. If you want to see the proof of this, I'm referring you to Lauder's mini course next week. He told me that he would do the proof of this during his mini course. And okay, probably he will, but you will see that this is not trivial at all. And remember, the obstruction to being generated by a curve was something like a curve winding around a disk and swallowing the disk in time 0, but in a non-localized way. And this was possible as soon as the driving function was not Hölder 1/2 with small enough norm. And here, because you take Brownian motion, the Brownian motion is not Hölder 1/2. So you really need to prove something. And well, you'll see the whole details, but essentially you need to show that even though the Brownian motion is not Hölder 1/2, it oscillates fast enough that on average, if you solve this, somehow you are measuring an average of beta t if you are away from the boundary. And if you average, it becomes a little bit better than Hölder 1/2, and you get the existence of the path. So that's more or less the basic idea behind the proof, but the details are very involved. Okay, so if you don't want to believe me that there is a path, then you can always read everything I will tell you about gamma as something about the union of the boundaries of the KTs. So I will tell you stuff about the trace gamma, typically gamma between 0 and plus infinity. That's the whole trace of the process in the upper half plane. Well, this is exactly the same as the union for t positive of the boundary of KT. And let's say, to make it precise, R union this is the same as this union R. So everything you can say about gamma, well, you can read it as information about the union of the boundaries of KT, and then you don't need this theorem to say something non-trivial about the process. Okay, so the second thing I said yesterday on Friday was something about the scaling properties of SLE, the scaling properties of the Loevner's equation, because so we have this theorem. We know that if we start from a discrete model and we take a scaling limit, then there is a parameter kappa such that the scaling limit is an SLE with this parameter kappa. And the question was, okay, but maybe kappa is not relevant either, because essentially it's a scaling, and if you scale the picture, maybe you will go from one kappa to the other. And so maybe kappa is not relevant. And a very related thing is this, that if you take SLE kappa in the upper half plane, and this is one feature that SLE in the half plane has, which SLE in the disk does not have, so that's one way in which this one is simpler, is that in fact SLE is scaling invariant. So SLE kappa, let's say, has Brownian scaling. Which means that if you look at gamma t as a curve, you can scale time by lambda squared and renormalize in front by 1 over lambda. Like you would scale a Brownian motion, and these have the same distribution. So this is a statement of invariance of the curve and the scaling. But of course, you need to reparameterize because the time parameter is determined by the size of the compact set. So this scaling appeared when I told you about the origin of this equation here. When you look at the map that removes lambda squared times k, this was not affected, but this was multiplied by a constant which depended on lambda. So it's the same lambda here. And so the proof is actually very easy. The proof is the following, that if you look at this guy, so that's a curve, so 1 over gamma, 1 over lambda, gamma at time lambda squared times t. This is a curve in the upper half plane in H, maybe H union a boundary. And because of the computation I did, we know that it is parameterized in the natural way so that the capacity or the size of this up to time t is exactly equal to t. So the time parameter is taken care of by the fact that we are multiplying by 1 over lambda in front here. So we know that if we look at ht, which goes from h minus this, 1 over lambda gamma between 0 and lambda squared t back to h, we know that this satisfies Lovener's equation for some driving parameter. So this satisfies Lovener's equation, but there's a driving function, which I want to call beta tilde t, but this is always defined as the image of the tip, so it's always the same as ht of the tip of this, and the tip of this is 1 over lambda times gamma times lambda squared t. 1 over lambda gamma at times lambda squared t. Now, again, because of the scaling properties of conformal maps, ht removes exactly this. So we know that ht is given by, so ht of z. What do you do if you want to remove this? Well, you multiply by lambda, you remove lambda squared times k, and then you divide by lambda. So we find that this is 1 over lambda times g at times lambda squared t of lambda z. So this map has the right expansion at infinity. It removes what you need to remove. So you know that by uniqueness, this is exactly the same as ht. And then, well, if you compute the image of this by this map, well, you find that you will end up with g lambda squared t of gamma lambda squared t. And then there's a factor 1 over lambda in front. So beta tilde t is 1 over lambda times beta at times lambda squared t. So that's the scaling property of the SLE. If you look at SLE and you rescale it by a factor lambda, and you rescale time by lambda squared, you can identify the driving process, and it's exactly the initial driving process with the time change here and the scaling in front. But now, because the driving process is a Brownian motion, this has the same distribution as beta as a process. So the scaling properties of Brownian motion give you exactly the same scaling properties of SLE, just by uniqueness of the conformal map. And in particular, you cannot get rid of kappa by scaling, because kappa is preserved by the scaling. OK, there's one other thing that you can use scaling invariance for, and that was maybe something I used without saying last week. Sometimes you want to look at exploration processes, or you want to look at discrete models in a domain which is not the domain in which Lovener's equation makes sense. You might want to look at the exploration of percolation in the domain which is not the upper half plane. Or you might want to look at Lupier's random walk in something which is not a disk. And I told you that there was conformal invariance in the discrete model. So you expect that the scaling limit of the exploration path, for instance, is invariant under conformal maps. So you expect that if you take any domain, so if you take omega simply connected, and say you take A and B different points on the boundary of omega, and I'm always assuming omega to have a smooth boundary and to be bounded and all the topological assumptions you want on it, you may want to define the exploration of percolation from A to B on a discretized version of omega. So you just take your favorite lattice here, you look at critical percolation, you explore it between A and B. So you put a boundary condition which is open here, closed here, all the way to the other side, like this. You explore the boundary, and you get a curve from A to B in the domain, something like this. Then you go to the scaling limit, and because of conformal invariance, you expect this to be some random continuous curve in the domain from A to B. And you expect this curve to be the image, by conformal invariance, to be the image of an SLE in the upper half plane by a conformal map from H to this domain. So that's very good, but maybe you want to do a little bit more. Maybe you want to see this curve as some kind of process indexed by time. And you want to define SLE inside the domain omega as opposed to SLE just in the upper half plane. So how to define caudal SLE in omega from A to B? So you are given omega, which is the domain here, and you want to define a process indexed by time living inside this domain and with a natural time parameter. So of course you may want to say that you will do the same as in the upper half plane. You start with an initial segment, you map it back to omega, and then you find a vector field that removes something infinitesimal, and then you hope that something will be explicit. But there's no hope of doing that in a general domain. It will never be explicit enough for computation, for instance. So the only thing you can do is take phi that maps omega to H, that maps A to 0, and that maps B to plus infinity. So that's a map uniformizing this domain to the upper half plane. So in the upper half plane, we know how to define SLE. So you start with SLE in H, and you say that SLE in omega is just the pullback by phi of SLE in H. So to define SLE in a domain, you just define it in a domain by conformal invariance by saying that there is one reference domain in which we know what SLE is, and then we can map it to other domains by conformal maps. So this a priori does not make complete sense because phi defined like this is not uniquely defined. You see that here we need to fix 3 real parameters, and here we have only 2 boundary points, so that fixes 2 real parameters. So if there is phi tilde, which is also doing like that, well, it turns out that because you arrive in H, they are conjugated by a conformal map from H to itself, fixing 0 and infinity. And these are exactly the scalings by real parameters. So if phi tilde does the same, then phi tilde has to be equal to lambda phi, where lambda is positive. So now if you want to define SLE in omega using phi tilde, you will look at the pullback by lambda phi of SLE in H. So that will be lambda minus 1. Well, that would be lambda phi minus 1, which is phi minus 1 of 1 over lambda times the SLE in H, something like that. But now, because we know that SLE in H is scale invariant, what you get here, this 1 over lambda does not affect the law of the curve up to a time parameterization. So what you end up with is that, in fact, this definition of SLE in omega as the pullback of SLE in H by any conformal map here is well defined up to time parameterization. So that will be the definition we will use. SLE in omega is well defined up to the parameterization. But that's okay, because most of the time when we look at SLE, we will forget about the parameterization. Remember that what we are interested in is the geometry of an interface. And this geometry has no time. The introduction of time here was a bit artificial to obtain the differential equation. But in most cases, we look at the curve not until a fixed time, but until a hitting time of something or until a stopping time. And then you will see that whatever you define as SLE in omega, so whatever phi you choose here, you will get the same thing. So SLE in omega is not completely well defined in the sense that there is no natural time parameter, but it's well defined enough for all we want to do with it. So just while I'm erasing the board, you can do the same thing if you want to define radial SLE in a domain. So you take omega, you take a point on the boundary, and you take a point inside the domain. And if you want to define radial SLE in omega, well, you will have to find a map phi mapping omega to the disk, and mapping the boundary point to 1 and the interior point to 0. And then you will define radial SLE in the domain as the pullback of radial SLE by phi. And now actually things are a little bit better, because this normalization of phi, fixing the image of one interior point and one boundary point, that's enough to make phi unique. So that makes radial SLE in a domain well defined up to time parameter. You also have the time parameterization defined for you. So in that sense, radial SLE is a little bit more rigid somehow. And so it's easier to define it in a general domain. OK. So that was the first non-trivial feature of SLE. And it will not, well, we'll not really use it, but it has the same scaling as run in motion. And that's to be expected of a scaling limit, because scaling limit is defined as the limit as the scale goes to 0, so it cannot really depend on any scale anymore. So remember, we started with the discrete model, and we obtained SLE. The most natural question now is how to figure out what kappa is. So the question is, who is kappa? So let's say I'm looking at percolation, and assume that I know somehow how to prove that the scaling limit of percolation is conformally invariant. So I know that the scaling limit is an SLE. I know that there is a parameter kappa such that the limit is SLE for the driving process, which is square root of kappa times bt. But so far, there is nothing telling me what kappa is, how we can read it from the model. So let me draw a picture, and then you will see that if you can compute something for SLE, then you can figure out what kappa is for any model. So there is one thing we know how to compute in the case of percolation, is the probability in the scaling limit that there is a crossing of a rectangle by an open cluster of critical percolation. Something like that, where this is lambda and this is 1. This, as the mesh of the lattice goes to 0, this goes to some function of lambda, which was explicit. And this was Smirnov's theorem that I explained to you on during the first course, at the end of the first course. And this f, in addition, is conformally invariant, and I told you a few things about it. So if you can compute the probability of some event that is related to SLE and which is related to this event in a natural way, then you can maybe match the parameter and find kappa such that you find the same f here. And if you can find such a kappa, then it will tell you that this has to be the kappa corresponding to percolation. So remember what we did to figure out if there was a crossing like this. One possibility was to start from the corner here and look at the exploration process of percolation, leaving red sides on the left and yellow sides on the right. So there was this exploration process that was always having a red curve on the left and a yellow curve on the right. So to do that, one way was to define a boundary condition with yellow here and red here. And then if this curve is gamma with scale delta, then this event that there is a horizontal crossing of red vertices, this is equivalent to saying that gamma touches this part of the boundary before touching this part of the boundary. If you have a horizontal crossing, you cannot touch the top before you touch the right side here, because the crossing will force you down, and it will lead the exploration path all the way here. And if you don't, that's because you have a vertical dual crossing, and the vertical dual crossing will push you from the right, and it will make gamma touch the horizontal side here before it touches the vertical side. So that tells you that whether there is a crossing or not can be read in terms of the exploration process. And the probability here is the probability that you touch this side before you touch that side. Now, the good thing about this formulation, at the discrete level, it's trivial that this is true, but it makes sense in a continuous case. If you assume that gamma at scale delta converges as delta goes to 0 in distribution to an SLE for some value of kappa in this domain from point B to point D here. So from B to D in the rectangle. This is more or less what the Smirnov theorem tells us, that there should be a scaling limit. It should be conformally invariant, so it should be an SLE in this domain. And it should be an SLE from this corner to that corner, just because that's where the exploration starts and that's where it ends here. So we want to estimate kappa, and if there is convergence, it tells us that f of lambda is the probability that SLE kappa, this SLE kappa in this domain, touches this part of the boundary. So let me finish here. I will call this C, and I will call it A. So touches the segment CD before it touches the segment AD. So this is what you get as an interpretation of the scaling limit. Cardy's formula, so the function f, should tell you with which probability you touch a given part of the boundary of a domain before another part of the boundary of the same domain. So if we can compute this for SLE, and if we can match the formula with the f that comes from Smirnov's theorem, then we are in a good position, because there will be such a kappa. We know that there will be such a kappa, but it will tell us which kappa it is, and it will identify the scaling limit of percolation. So the aim, so that's the first computation we'll do for using SLE. So the aim is to compute this probability for SLE kappa. So the first remark is that for this to make sense, you need the SLE curve to touch the boundary. So we first need something. We need gamma to touch the boundary of the domain. If gamma does not touch the boundary of a domain, then we know that it will not be the scaling limit of percolation, because percolation will cross the domain by Rousseau-Simon relation. And then if it doesn't touch the boundary, well, we cannot look at these stopping times here, so there's even no way we can start doing any computation. So the first question, well, the question number 0, before we determine what kappa is for which values of kappa we touch the boundary, and for which value of kappa we don't touch the boundary. So the question -1, so for which kappa does SLE in H. I will do it back in H because that's exactly the same question because of what I told you about SLE in domains. So for which kappa does SLE in H touch the real line? So that's the first question, and if we can answer this, then we can then start in the regime where you do touch the boundary. We can start doing other computations which are a little bit more fancy. So here, I will go very quickly because that's something you did already in an exercise session. Maybe you didn't notice that that's what you did in the session, but you will recognize the computation very quickly. So here's what we're going to do. We want to know if the curve gamma touches the boundary. In fact, what we'll do is we'll fix a point on the boundary, and we'll try to determine if you touch the boundary to the right of this point. So if you imagine a picture, there is a point at the right of 0. And if the curve gamma touches the boundary on the right of this point, it means that whenever it touches on the right, it will close a loop that contains this point. I'm cheating a little bit when I say that, but essentially that's the idea that you should have in mind. So what it means is that if you look at what happens for the time just before you close the loop, you will see something interesting happening. So here's the picture you should have in mind. This is 0. This is a point x. And we want to know if the curve touches to the right of x. So we want to know if this occurs like this. So this is an SLE. So assume this occurs at some time tau, and look at what happens at time tau minus epsilon. So this is time tau minus epsilon. So at time tau minus epsilon, we can look at the map, at the conformal map G, at time tau minus epsilon. So it removes the whole yellow curve here all the way to the tip. So it maps this back to here, like this. It maps the tip somewhere. But if you look at the harmonic measure from infinity or from a point which is far away on the boundary of this, well, you'll see that if you launch Boden motion from here, it's very likely to touch on the left side of the curve, but it's very unlikely to touch on the right side of this part of the curve. It's very difficult for Boden motion to enter inside here and touch anything inside. So that will tell you that the whole harmonic measure of the inside of this loop here, all the way to the opening, is very small. And because harmonic measure is preserved by the conformal maps, it tells you that the image by G of the whole inside here will be very small here. So the first thing it tells you is that the image of the tip is very close to the right side of the interval. So it tells you that beta tau minus epsilon is almost at the right of this interval. And it tells you that the image of x is also very close to the tip because x is inside the loop. So this here is g tau minus epsilon of x. And of course, as epsilon goes to 0, this distance here becomes shorter and shorter because the harmonic measure of the inside of the loop is smaller and smaller. So what you have is that as epsilon goes to 0, g tau minus epsilon of x minus beta tau minus epsilon, this goes to 0. And it reaches 0 whenever you close the loop, because when you close the loop, the harmonic measure of the inside becomes equal to 0. And it means that everything is mapped to the same point. And the tip and x are both inside the loop, so they become equal in the limit. So what we end up with is that if you want to close a loop containing x, then this has to go to 0. On the other hand, because the curve is continuous and because you can prove some regularity for the curve, it turns out that this is an equivalence. It's not possible for this to go to 0 in finite time without closing a loop around x. So to figure out if you close the loop, it's enough to study this process here. So let's do this. And this is where you will recognize something you did in an exercise session. So define yt to be exactly this process here. So it's gt of x minus beta t. So it's some random process. It's equal to x at time 0. So maybe I will denote it by ytx to really write that it starts at x. So y0x is equal to x. And we want to know if ytx hits 0 in finite time. And if it does, then you close loops. And if you don't, then you don't close loops containing x. So to know if you touch 0 in finite time, well, we'll look at the infinitesimal behavior of this. And we'll see if this is solution to some stochastic differential equation. So what are the variations of ytx? d of ytx, it's composed of two terms. There's the variation of gt of x and the variation of beta t. Variation of gtx we know because it's solution to a differential equation in t. So this is a smooth function of t, and the variation is just dt of gt of x dt. And beta t is Brownian motion, so it has an increment which is an increment of Brownian motion. So if you use Leibniz's equation, we find that this is equal to 2 dt over gt of z minus beta t. That's exactly Leibniz's equation. Minus, and beta, we know that beta is square root of kappa times Brownian motion. So this is square root of kappa dbt. Okay, there is even no Ito calculus here, it's just matching the terms. Here, that's where the good thing happens, that gt of z minus, sorry, that's an x, of course, gt of x minus beta t, that's exactly the definition of ytx. So what you get is that this is 2 dt over ytx minus square root of kappa times dbt. So this is the generator of ytx. It tells you in particular that yt is Markovian. The evolution only depends on the location at time t. And then if you remember what Hugo told you last week, you recognize that this is a Bessel process. Maybe there's a linear time change to put one of the parameters here or here, but that's a Bessel process of dimension exactly 1 plus 4 over kappa. So I leave you as an exercise the fact that you can look at this, look at the definition of the Bessel process in the exercise session, and match the parameters to obtain that the dimension should be 1 plus 4 over kappa. So what you know of Bessel processes is that they have a different behavior if the dimension is less than 2 or if the dimension is bigger than 2. So let me put that this should be equal to d. So if the dimension is large, if d is at least equal to 2, and this means that kappa is at most equal to 4, then you know that the Bessel process does not hit 0. yt does not hit 0. So what you know is that SLE does not swallow x, so SLE does not touch anything to the right of x. You cannot reach 0, so you cannot touch the axis to the right of x. So that's true for all x, which means that SLE does not touch the real line except at 0 at time 0. That's the only thing that can happen. OK, then, in fact, it implies a little bit more. If you look at k at time t, so from this, we know that it doesn't touch the real line anywhere except on 0. So this is typically what kt could be. This is gamma t. Then we know that what happens after that is just SLE in the complement. So the future of gamma is something like here. So we know that the future does not touch the boundary of h minus kt. That's what you get here. You don't touch the boundary of the domain you live in. So this implies that gamma between t and plus infinity does not touch the boundary of h minus kt away from gamma t. The only place where the future can hit the boundary of the past is at gamma t at time t. And this is just the same statement, except you do it at time t instead of doing it at time 0. So what it tells you is that essentially any point on the curve is a cut point. And this implies that gamma is a simple curve. It has no double point. It cannot touch itself, because whenever it would touch itself, it would create a loop. And we know that we don't create a loop. OK, there's a little bit of, well, it's not as fast as this because there are uncountably many times, but essentially that's the argument. OK, so that tells you that for kappa up to 4, gamma is a simple curve. Now the other regime is when the dimension of the Bessel process is less than 2. So if d is less than 2, meaning that kappa is bigger than 4, then you know that the Bessel process will touch 0 in finite time, almost surely. So yt does hit 0. And so there is a time such that x belongs to k tau. And this time is whenever you hit 0 with your Bessel process. So what it tells you is that the curve does touch to the right of x. This happens whenever, so this is x, this is 0, and this is gamma tau. So in this regime, gamma does touch the boundary. And then the same argument here tells you that not only do you touch the boundary, but you touch the boundary of your past at every scale. And so gamma is not a simple curve. So there is this phase transition at kappa equal to 4. Below 4, you are a simple curve. And above 4, you look something like this. So you will create loops at every scale, and you will close them, and it will look something like that. So let me finish the picture of the phase transition and sum it up as a proposition, and then I will come back to the crossing probability. So this is what we get. And in fact, I will make an additional statement in this theorem, but I have no time to prove it. So if you want the proof, you will have to go to the exercise session number 6, I think. is that something else happens not at k equal to 4, but at k equal to 8. And I will just state it here. So here's the theorem. If kappa is between 0 and 4, the curve is a simple curve. If kappa is between 4 and 8, then it's not a simple curve, but it does look like this. And if kappa is bigger than 8, it's even worse, in the sense that the curve will in fact be space-filling. So here's the statement, theorem. So if kappa is at most equal to 4, then gamma is almost surely a simple curve. If kappa is strictly between 4 and 8, then gamma is not a simple curve. So gamma has double points, but it has 0 Lebesgue measure. So somehow it's still a nice curve. It has double points, it has loops at every scale, but it has no positive measure. And in fact, in both cases, the Hausdorff dimension of the curve is equal to 1 plus kappa over 8. So this tells you that something should happen at kappa equal to 8 when you reach the dimension of the space. And if kappa is at least equal to 8, then gamma is actually almost surely space-filling. And by that I mean that every point is on gamma itself. Not on the closure, but really gamma is onto. So in the picture, this looks like this. The intermediate regime looks like this. And the last regime looks something complicated like this. And of course the dimension is 2 because you contain every point. So this is what we get when we want to know if the curve touches the boundary. So let me come back to the initial motivation. We want to look at crossing probabilities. And for these to make sense, you need the curve to touch the boundary. And so you need kappa to be bigger than 4. So for the computation of the crossing probability, we will restrict to the case where kappa is bigger than 4. Okay, I will erase this. So this was the first phase transition. The second phase transition at kappa equal to 8, you will see in the exercise session, I think on Thursday. Okay, so now we look at SLE for kappa bigger than 4, and we want to compute something that looks like a crossing probability. So to make things simpler, instead of looking in a rectangle, I will look in the upper half plane, knowing that anyway we can relate them by a conformal map, so we'll be able to go back to the rectangle eventually. And so we want to compute something that looks like a crossing probability in the upper half plane. Okay, so we need to have a setup that looks like a rectangle. And it turns out that the natural thing to do is exactly this. We live in the upper half plane, we start at 0, and we'll fix 2 points, one on the right and one on the left, which will play the same roles as A and C here. The starting point will be at 0, the target point will be at infinity. And we want to know if we touch one interval in the boundary before the other one. So here's the picture. I'll pick the same notation as I have in my notes. So the notation is that A is negative. So I'll pick A negative and C positive. So you should think that this is at infinity, this is 0, so this is negative and this is positive. And we want to know the probability of the event EAC, where EAC is the event that you touch, say, to the right of C, let me do it right, to the left of A, and you touch minus infinity A before touching to the right of C. So in the picture, you have something like this. This is H. You start at 0. There is a point A here. There is a point C here. And you want the probability that the exploration curve, or the SLE, touches here before it touches on the right of C. So that's actually reversed from this, but if you can compute one, you can compute the other one. And they will solve essentially the same equation. Okay, so this is what we want to compute. So the first remark is that we know that SLE is scale invariant. We just proved it half an hour ago. So this probability of EAC is a function of the ratio C over A. If you rescale the picture, the only invariant is C over A, and so this probability has to be a function of this invariant here. And in fact, for practical reasons, it's better to write that P of EAC will be written as some function of minus A over C minus A. That's the same information as the ratio C over A. So there is a function f such that this is the case. And the question is how to compute f. So you did something like that in the case of the Bessel process when you looked at the probability of exiting an interval on the left or on the right, and it gives rise to a differential equation on f. So the first step is to assume that f is C2 and see if we can find a differential equation satisfied by f. So find an ODE for f. So the second thing we want to do is to really use the fact that we're looking at SLE. So far this is not specific to SLE. It's any configuration, any setup which is scale invariant will satisfy this. So we need to put SLE in the picture. So here's how you can do that. Look at the process up to time t and assume that for the moment t is very small. Assume that t is small enough that it's not possible to have hit to the left or to the right, or that this probability is very small. What you can do is then map this picture by GT. And so it will map three interesting points. There are 3 points that are special in the picture. There is gamma t, there is A, and there's C. And you can look at the image of this by GT. So you'll find something like that. This is the image of gamma up to time t, and this is beta t. And then C is mapped somewhere here. So that's GT of C. A is mapped somewhere here. So this is GT of A. And then the conditional probability to touch on the left of A here before you touch on the right of C here, given that you still have not touched by the time t, is the probability that this part of the curve here after gamma t touches on the left before it touches on the right. If you map the picture, it's the same as saying that the image of the future here touches the image of the left here before the image of the right here. meaning that it has to touch to the left of gt of A before it touches on the right of gt of C. Okay, and then because the SLE has the Markov property, we know that what you have here, if you shift everything back by minus beta t, this is exactly an SLE starting here, and you want to know if it touches to the left of here before it touches to the right of here. But this is the definition of f. The probability that you do that is exactly f of minus a over c minus a, but now a and c are shifted by beta t. So a becomes gt of a minus beta t, and c becomes gt of c minus beta t. So this becomes beta t minus gt of a divided by gt of c minus gt of a. So that's the conditional probability given what you have up to time t and given that you still have not touched outside of this interval, that eventually you touch to the left of A before you touch to the right of C. So this is a conditional probability, so it has to be a martingale. So this is a local martingale. This is a martingale. This is the same argument as you saw in the case of the Bessel process. So this is a martingale. So if you look at the variation of this, well, you can apply Ito's formula. You can compute df by Ito. Write that the drift term, that the term in dt is equal to 0. And this is a differential equation satisfied by f. So what you end up with, okay, I'm taking more time than I thought, and I really want to do some other computation before the end, so I will just write what you get. So what you get is that in the end, the equation you get is kappa over 4 times f double prime x plus something like 1 over x minus 1 over 1 minus x f prime of x is equal to 0. So this is the equation you get. And if you solve it, what you get is that f of x is integral from 0 to x du over u to the power 4 over kappa 1 minus u to the power 4 over kappa. So this is, and maybe there's constant in front so that it becomes equal to 1 at the boundary. Okay, so this is what you get by solving this equation and saying that the boundary condition is that if you start at A, you do touch to the left almost surely before you touch the right of C. So f should be 1 here and should be 0 here. And if you can map, if you match what happens here, you'll find that it works and that the boundary conditions are the right ones. So this is how you can compute crossing probabilities using SLE. And I realize I'm going a little bit too fast, but it's maybe better for you if I don't do all the computations on the board. If you want to do them, they are not very difficult. And so you find this. So how do you match with the results for percolation? Well, somehow you know that for percolation, f can be written in terms of a conformal map from the domain to the equilateral triangle. So it tells you that here, the kappa corresponding to percolation should have something to do with an equilateral triangle. So there should be powers of 1/3 somewhere, and it should look like a Schwarz-Christoffel map. Christoffel from H to an equilateral triangle if kappa is the right one for percolation. It turns out that if you want to write the map from upper half plane to a triangle like this, well, this tells you that kappa should be equal to 6. There should be a u to the power 2/3 here, so that if you integrate, you find something like a 60 degrees angle. So this is a posteriori motivation. If you don't know about Schwarz-Christopher maps, you can just say that you compute this from the Kadis-Smirnov formula. You map it back to the upper half plane by doing explicitly a conformal map from the rectangle to the upper half plane. And you find that you find exactly this with u to the power 2/3 times 1 minus u to the power 2/3. So this tells you that if percolation has a scaling limit, and if this scaling limit is conformally invariant, then it's an SLE, and then it's SLE for kappa equal to 6. So the natural conjecture is that percolation converges to SLE 6. And it turns out that this is the case. And if you look at the argument I gave you for the conformal invariance of Brownian motion, you can already prove that the shape of the exploration process, whenever you reach here, so there is the lowest crossing, which is the lowest red curve here. Then the shape of this will converge to the boundary of SLE6 whenever the SLE6 touches this part of the boundary. So why is that? Because the probability that you avoid an obstacle here is exactly the probability that you cross the complement of this, and crossing the complement of this can be computed by a conformal map. So that's the same argument as showing that Brownian motion was conformally invariant. You find that the crossing probabilities in any subdomain will match because they are conformally invariant. So this tells you that the shape of a percolation cluster from the outside is encoded as an SLE6. This just for the from Smirnov's theorem about crossing probabilities. What happens inside and whether the exploration curve converges to the trace of an SLE, this is more complicated because it's not just a computation of crossing probabilities. You need to prove tightness, you need a lot more of technicality. And this is what was done by Kamiya and Newman a little bit later. So mainly there is one estimate, which is the crossing probability, and then there is a tightness result showing that you converge to the trace. Okay, so that was the first computation that was possible to do with SLE. And it allows us to identify the value of kappa corresponding to percolation, because we can compute the probability of the same event in two ways. Once from percolation by Smirnov and once using SLE. So what I will tell you tomorrow is that this is not the right way to identify kappa equal to 6 for percolation, because SLE for kappa equal to 6 is really something special, and it is so special that you don't need this computation to really prove that it is the unique possible scaling limit for percolation. But what I want to do now in the last 20 minutes is another computation which is a little bit deeper than that. And what I don't have time to do, you will have time to do in the exercise session this afternoon. So it's maybe paragraph number 2, which is critical exponents. So what I want to tell you is more or less how to use SLE, not to compute a crossing probability, but to compute a critical exponent for a discrete model. So the aim is this. So you know that if you look at percolation on the triangular lattice, or in colorings of hexagons here, in a large ball, you know that the probability that there is an arm going from 0 to the boundary, if this is size n, well, you have heard several times last week that this is bounded above and below by n to some positive power. And maybe it was even stated at some point that this had exactly a power law decay. And in fact, what turns out is that as n goes to infinity, for critical percolation, this behaves exactly like n to the minus 5 over 48. And it's equal to this plus little O of 1. So the goal of what I will tell you now and the exercise session this afternoon is to prove that this is indeed the case and to show you how to compute such an exponent here. So it's a little bit more involved than computing crossing probabilities, but the main idea is the same. You use SLE, you obtain differential equations, and you solve them explicitly. So the other thing that I will tell you is this, because the computation is exactly the same, almost to the end, that in the same setup, okay, maybe it's better if I do it on the side. In the same setup, you can look at the probability of existence of not one arm, but a little bit more than that. And there is one case for which the computation is not more difficult than that. It's the case of two arms. So the probability that if you look at critical percolation in the same disk, you have one arm which is open and one arm which is closed from the center to the boundary. So the probability of this behaves like n to the minus 1/4 plus little O of 1. So this is the kind of results that we want to prove. We want to know what SLE tells us about events like this. Okay, and of course, we are going to assume a few things. So we are going to assume that indeed percolation converges to SLE. And I'm going to cheat a little bit. I'm going to assume that the exploration of percolation in a disk converges to radial SLE6. And I'm not going to tell you what the exploration of percolation in a disk is. But if you think about it, there is a problem because there's only one boundary point if you want to look at SLE6. But you need two boundary points to make a boundary condition for the exploration process. So let's say that, well, it's not difficult to make sense of this, but I choose not to make sense of this for you. And I want to state these two things as statements on SLE itself. And then going back from the SLE statement to a percolation statement is something that is not very difficult to do. So the goal is to obtain the 5 over 48 as quickly as possible, and then the rest is just putting the pieces together. So the rest does not contain much more information than what I will tell you just now. Okay, so here's the intuition. I will draw the picture in the case of the two-arm event. So what's the probability that you have two arms, but in addition to that, the red arm touches on the bottom half, and the yellow arm touches on the top half. So by Rousseau-Semmelweis, it's the same order of magnitude. You can always take an arm and move it to touch somewhere else on the boundary by taking a little tube. So if you can estimate the probability of this, then we are done. It's essentially the same thing. So what it tells us is that if you start the exploration process here, then the exploration process will touch the origin before it touches, say, this point, or before it makes a loop around the origin that separates the origin from the circle. And that's an equivalence. This event, so the event that there is a red arm going to this half and a yellow arm going to this half, okay, this is equivalent to the fact that the exploration process touches the circle of mesh 1 delta around 0 before disconnecting 0 from minus 1. So before disconnecting zero from minus 1. So it's an equivalence. If this occurs, then you reach here, and of course you can still reach minus 1. On the other hand, if you do touch here before without disconnecting, then the boundary of the exploration at this point gives you exactly the path you are looking for. So that's an equivalent. And again, now we are happy because this event makes sense for SLE. You can look at a radial SLE in a disk, fix delta positive, forget that there was a discrete model, so forget that delta was the mesh of a discrete lattice, look at radial SLE, and compute the probability that this occurs for a radial SLE in a disk. And then hopefully, once you do that, then you can come back to a discrete model after that. So the goal is to compute the probability that this occurs for radial SLE. And I'll do it for any kappa because the computation is the same for all kappa. So again, if you want this to make sense, you need that this connection is something possible. So you need the SLE to make loops. And that means that you need kappa to be bigger than 4 again. Here I showed you that there was a phase transition at kappa equal to 4 for caudal SLE. But the way we chose the equations for the radial and caudal SLE, this 2 in the equation for caudal SLE, which is not on the board anymore. So this ensures that the phase transition at kappa equal to 4 is the same for caudal and radial SLE. And it means that we are going to look at this for kappa bigger than 4. So for kappa less than 4, it will be a simple curve. You will reach delta without ever touching the boundary or without touching your past. So you cannot possibly disconnect 0 from minus 1. And this probability is equal to 1. So it doesn't make sense to look at this for kappa less than 4. How do you compute this? Well, we'll do the same kind of reasoning as in the case of the crossing probability. We'll look at a given configuration. We'll see what happens if you look at the process for a little time. And we'll figure out that something should be a martingale and write a differential equation on something that will play the same role as f here. OK, so let's do it in the picture. We start SLE from 1 because it's a radial SLE. And let's look at what happens in a very small time. So this is the circle. This is 0. This is 1. And you start the SLE for a small time here. And again, for the picture, I'm assuming that the time is small enough that you have not disconnected minus 1 from 0 by time t. So this is minus 1. And t is very small. So there is one conformal map that I want to use. The only one that is in the picture is GT here. And OK, maybe I should clean this a little bit. So GT maps the complement of the curve back to the disk. That's OK. It fixes 0 And we need to figure out what it does with -1. What it does with -1 is it will send it to GT of -1. So here's the picture. This is the disk. 0 is fixed. You map this part of the boundary to somewhere here. This is beta t. And this is GT of -1. So this is 0. The derivative here is positive. OK, so this is the picture, and I will argue the same way as before. So assume that at some point you disconnect 0 from -1. How can it occur? Well, it means that you make a loop around 0 like this. And the moment you make this loop, the harmonic measure of the outside of the loop seen from 0 goes to 0. Because you are trapping Brownian motion from 0, it's not possible to escape anymore. And what it means is that the image of -1 becomes very close to the image of the tip of the curve. Because the harmonic measure of the interval on the boundary between this and this is very small, because Brownian motion is trapped. So it's the same picture as this, except that instead of going from here, you go from the center of the circle, but it's the same idea that if you close a loop, then the images of boundary points outside the loop are mapped to the same point. So what it means is that whenever you close a loop, so closing a loop is equivalent to having GT -1 minus beta t going to 0. GT of -1 minus beta t going to 0. So we are essentially in the same setup as before. If we can compute the probability that GT of -1 minus beta t does not reach 0, then we'll obtain an estimate on the probability of not closing a loop. And not closing a loop exactly means not disconnecting 0 from -1. So this is the event we want. So as it turns out, there is one thing you can look at. By continuity, you can always measure this angle here. So define theta t to be the angle between beta t and GT of -1. So theta t is a continuous function. And if you apply Ito's formula, and this is a little bit nasty, but it's a good exercise, what you get is that d of theta t is square root of kappa times dbt plus cotangent of theta t over 2 dt. So this is what you get as a generator for the angle between GT of -1 and beta t. So this, now if you know about stochastic calculus, you are very happy, because this is a diffusion in the interval 0 to pi. And you are interested in the probability that you touch the boundary at some time before doing something. So we want to look at the behavior of this diffusion, and you want to know if you touch the boundary. So there is still one thing I need to tell you. It's how delta comes into the picture. But this is very easy. What is the first time when you hit the circle of size delta here? Well, what you know from the exercise session number 3 is Kuiper's 1/4 theorem, which tells you that if you map the complement of the curve here back to the disk, the derivative of g at 0, which is e to the t, So e to the t. That's gt prime of 0. Well, this up to a constant which is 4 on one side and 1 over 4 on the other side, this is the same as the ratio between the distance to the boundary here and here. That's Kueber's 1/4 theorem. The distance to the boundary here is 1. And the distance to the boundary here, whenever you reach the circle of radius delta, it's exactly delta. So if I look at tau delta, which is the heating time of this circle, e to the tau delta up to constants is the same as 1 over delta. That's Kueber 1/4. 1/4. So that means that tau is exactly the log of delta plus big O of 1. So tau delta is log of 1 over delta plus big O of 1. And that means that the probability that you reach radius delta without disconnecting is the same as the probability that this diffusion survives in this interval without touching the boundary for time log 1 over delta. So the probability of non-disconnection is the probability that you survive here in terms of the diffusion longer than log of 1 over delta. So now we are back to a problem in one-dimensional diffusions where we have an explicit diffusion here, and we want to know the probability that it survives longer than some given time. So this is very classical, and I want to just write what you get if you do the computation, and then the computation you will do it this afternoon during the exercise session. So the general idea is that if you have a diffusion in an interval, and the interval is bounded and the diffusion is not too nasty on the boundary, the probability that you survive for time bigger than t should behave like e to the minus lambda t, where lambda is the leading eigenvalue of the generator of the diffusion. So what you are looking for is some function f on the interval such that if you look at f of xt times e to the lambda t, this is a martingale. So you are looking for an eigenvalue lambda and a function f. So the problem is this. Find lambda positive and find f from 0 to pi to r plus with the appropriate boundary conditions in such a way that f of theta t times e to the lambda t is a martingale. So this is what you get as a variational problem somehow. You will have that the survival probability of this diffusion then behaves like e to the minus lambda t. So in the case of the two-arm exponents, it turns out that you can find that f of x is sine of x over 2 to the power of something like 1 minus 4 over kappa. And you will find that lambda for the two-arm event is equal to kappa minus 4 over 8. So this is what you will do this afternoon in the exercise session. If I still have 1 minute, I will do the picture for the one-arm exponent because that's something that I want to show you and I don't want to take too much time in the next session. But that's just one picture and one sentence. So what does it mean now that you have one red arm going from the boundary to 0 in terms of the exploration process. So it doesn't mean that you reach radius delta without disconnecting, because that imposes two arms. That's much more unlikely. So what happens is that if you are following, say, the red on the left and the yellow on the right with your exploration process, assume that you are closing a loop clockwise. So I assume the picture is like this. And assume that you are exploring like this. And you close a loop like this before you reach the radius delta. So really, you are following red on the left and yellow on the right. So the picture looks like this. Like this. There's the red inside, like this. And then you continue here. So if you look at the picture very closely, you will see that this does not prevent a red arm from going inside. The red arm is connected. The yellow here stops, but the red continues. And if you turn the other way, it's the opposite. One color will cross, but that will be the yellow one. So if you want a red arm from the boundary to the inside, you are allowed to close the loop in one direction, but not in the other direction. So the event becomes, in terms of SLE, that you reach radius delta before closing your first loop clockwise around 0. And in terms of diffusion, that becomes you survive for the diffusion which is allowed to touch one side of the boundary. So you have this diffusion, but it's reflected at 0. And you want it to survive because before it touches 2 pi. But as the same, you do the same computation. All that changes is the boundary conditions you want for the function f. Here it was a Dirichlet boundary condition. You were killed on both sides. If you want the probability for the one arm, you will look for a function f, which is 0 on one boundary and derivative 0 on the other one, which is a mixed Dirichlet-Neumann boundary condition. So the function will be sine of x over 4 to some power, which is the same. And then the lambda you get from the computation is, I just write it and then I let you go for coffee. For the one arm exponent, so this exponent is the same, but you will have sine of x over 4 to the power of 1 minus 4 over kappa. And the exponent lambda this time is equal to kappa squared minus 16 over 32 kappa. So that's the kind of computation you can do if you are interested in critical exponents. And then if you are interested in percolation in particular, you just put kappa equal to 6. And here you find 1/4, and here you find 5 over 48. So that gives you the computation of the critical exponent for percolation. OK, so tomorrow I will speak more about the restriction property and the locality property. So two particular features of SLE for kappa equal to 6 and kappa equal to 8/3, and why they are even more particular than the other values of kappa. So thanks. Questions?